Assalamualaikum warahmatullahi wabarakatuh, and hi to my students. Welcome to the next video lecture of subtopic field, which is the last subtopic for chapter 5. In order for you to learn this video lecture, it is advisable if you look first from the previous video lecture, which entitled group, abelian group, and also ring. Because field is the largest algebraic structure that you learned, therefore it will be much more helpful if you understand the properties for the previous algebraic structure. Field. The definition of field is very simple. Field is just a commutative division ring. Therefore, we need to know first what is the definition of division ring. In order to assist you to understand, I present to you this simple visual diagram which can illustrate a ring, commutative ring, and also field. Okay, closed, associative, identity, unity, inverse, unit, commutative, left and right, distributive law. Okay, suppose if I define this symbol as ring, a ring must be abelian. Condition number 1. It must be closed, associative, it has identity, it has inverse, it must be commutative, the multiplication is associative and is satisfied, left and right distributive law. For a commutative ring, not commutative division ring, commutative ring, which I try to put this symbol to represent it, is just a ring such that it must also be commutative under multiplication as well. Therefore, it named as commutative ring. For field is a commutative division ring. In order for you to understand division ring, you must know the concept of unity and unit first. Okay? If the addition has identity, for the multiplication we represent it as unity. The definition remains the same for identity. For unity is the same definition. The difference for this one is just that the plus is specified to use the term identity. For the multiplication, the identity for the multiplication is a rebrand, I might say, as unity. But A times E is equivalent with E times A equals to A. Applies for both identity and unity. You can think unity as a special identity name for multiplication. For the inverse, same goes for this case. If the addition we use the term inverse, for the multiplication we use the term unit. So if we say identity, it means for addition. If we say unity is for multiplication. Identity inverse for addition, unity unit for multiplication. So, a division ring is basically means that the ring which has non-zero element, for non-zero element it has units. Okay, later I will show the difference between zero element and non-zero, whether we need to check whether it has a unit or not. Basically, field which I represent as this symbol. Okay, it must be a ring. It must be a commutative ring, and it must have, okay, if we have a unit for non-zero element, it must have a unity. Okay, we discussed this. Inverse, in order to have inverse, you must have identity. Therefore, it must have unity. It must have a unit, but I want to add for non-zero element only. Therefore, if we want to determine whether a given structure is a field or not, it must also have all of these properties denoted by star. Let's try to attempt to answer the actual question. Show that Z5 star is a field. Okay, I will discuss two questions. The first one is show 5 star Z5. Okay, is a field or not? Apparently, if you want to show this, this will be a very long solution. That's why in the previous exam question or even test question, we usually put by assuming that it is a ring. Okay, show that Z5 ring is a field. Okay, usually we don't write it this way. We will add one more by assuming this Z5 plus is a ring. Show that it is a field, or determine whether it's a field or not. If we don't put the top statement by assuming, then the solution, like the previous video lecture, it will be quite long. You need to show that it is a ring first, you need to satisfy 3 conditions, then you show it is a field. Based on the assumption that you already understand, know how to prove a ring, you need to prove whether the ring is a field as well. If you refer to the previous visual diagram summary, what more that needs to prove? Okay, if we assume that it is already a ring, so you don't need to actually show the previous properties. But for Z5, let me do the plus and multiplication Cayley table. So Z5 0, 1, 2, 3, 4, 0, 1, 2, 3, 4 plus okay, this is for plus. For multiplication, two times 2, 4, mod 5, 1, 2 times 4, 8, 3. 3, 1, 9, mod 5, 4, 3, 11, 12, 2. 4, 3, 2, 1. Okay, finished. Okay, what more that you need to prove? Okay, because a field is a commutative division ring, and division ring must show that you must have unity and it also must have units. When we talk about unity and unit, we focus on the multiplication part. All right, what is the unity for multiplication for Z5? If you refer this table, the unity is 1. Okay, and then you need to mention the inverse, the unit, sorry, the unit for every element there for non-zero element. Okay, for non-zero element, so it excludes 0. You don't need to find the unit for 0. However, I do need you to tell me specifically what is the unit for 1. The unit of 1 should behave like this. 1 binary multiply 1 inverse equal to 1 inverse times 1 equals to 1. So 1 inverse here such that it will produce the unity back is 1. For the 2 inverse such that it will produce 1 is 3. Okay, you can verify it on your own based on how to read the Cayley table. The unit for 3 is 2 and the unit of 4 is 4 itself. Right now it's a division ring because it has unity, and you must show that it must have units for every non-zero element. Right now, is it commutative division ring? A commutative division ring, you must look at the point of multiplication. Okay? Therefore, for the multiplication part, is it commutative? For the multiplication of Z5, I think we discussed this in the previous video lecture previously, is that the multiplication for Zn and even for Z5 is indeed commutative based on the properties of integer multiplication. The multiplication for Z5 is commutative. Therefore, as a large conclusion there is that the ring of Z5 is a division ring. It is also commutative, is a commutative. Okay, you can directly write it as a field as well, but okay, if I want to do this slowly, okay, it's a commutative division ring. Z5 is a field. Okay, I retrace back the step. We need to actually show that any algebraic structure is a ring as well, then we can show that it is a field. But for right now, by assuming that it's a ring, you don't need to show the ring part. You need to just to show the division ring part, and the division ring must be commutative. And division ring, you must have units for non-zero element, therefore you must have a unity. Next, we proceed by showing or even stating in a general term that is actually the multiplication is commutative, and if the multiplication is commutative, therefore it's a commutative division ring, therefore it is a field. Let's try to do one more example, this time which involves the ring of integer. Is it a ring? I'm sorry, I repeat back my question. I write it in a full sentence by assuming that this integer multiply. The ring of is a ring. Show that or even determine whether it is a field. Okay, for this question, we already know that the addition is abelian, so we already know that it is a ring, so we focus only specifically on the division ring and check whether it is a commutative under multiplication as well, but this time it involves the addition, the integer. Okay, for the integer, let me demonstrate you this one first. For every integer, okay, a times b, we focus on the multiplication part, and the unity for this z, okay, try to think like this. Does there exist an integer such that you take a, which is an integer, times e is equivalent with e times a, you get back a? For this one, for example, if a equals to 1, 1 times e equals to e times 1, you get back 1. What will be the value of e? Same goes for, apply for 2. 2 times e equals to e times 2, you get back 2. And if you follow this logic, the unity for the integer is 1. Okay, it's enough, unity exists. Okay, but for the part of units this time, units, the inverse for multiplication, does there exist a unit for non-zero element? For all non-zero element of the integer. Okay, let's check one by one. If the integer is 1, does there exist the inverse such that this happens? And you can say here that the inverse, the unit is 1. How about 2? Such that 2 times you get 1, commutatively first. And what will be the 2 inverse? Based on the properties of algebra, the 2 inverse is 1 over 2. However, 1 over 2 is not integer. The unit does not exist for 2 in the domain of integer. The unit of 2 does not exist. And this one counter example you can follow. There is no unit for 3, there is no unit for 4, there is even no unit for -1 and -2 as well. Based on this counter example alone, it can be shown that there does not exist a unit for all non-zero element of integer. Okay, therefore by this counter example alone you can already verify that this is not a field. But if the question, by checking all the properties of a field, again you need to also check for the commutative as well. Is it commutative? Is the multiplication of the ring integer is commutative? Okay, this is very simple. I can just say definitively that for every integer, a times b equals to b times a. Therefore, although it satisfies the commutativity, it does not satisfy the condition for division ring. What I can conclude is that this ring is not a field, because although it is a commutative under multiplication, it does not have a unit for every non-zero element of integer. This concludes the video lecture for field, but I ought to have an extra lecture again, extra bonus video lecture to help you understand, to answer the question more effectively. So I will create several more videos to enhance your understanding, specifically in the proving chapter and also the abstract algebra chapter. By then, I would like to thank you and goodbye. See you in the other video, bonus video.